2 seconds. Okay. Hello, everyone. Hello back. This is the part 2 of my talk for Nearly Carbon Neutral Conference 2022. I'm going to assume that you have seen the first part of the talk. If you haven't, I recommend you do. Thanks you again to the organizers for inviting me. And this is still joint work with Gabriele Viacci, and the pictures are still mostly due to Teddy and a big part due to me. So thank you, Teddy. So I recall the statements of our theorem, which is that there exists irreducible, non-symmetric, non-strictly convex, divisible convex sets in any dimension more than 3 or equal to 3. As I mentioned in the first part, this construction uses a bending procedure, which I explained in the first part. I am going to explain the construction in dimension 2, which may seem paradoxical because the theorem doesn't talk about dimension 2. So the construction does work in dimension 2, but the result is just not interesting and not strictly, and strictly convex. But it's much, it works and it's much easier to explain. Okay, let us start with, so we're going to construct a convex projective structure on the following genus 3 surface. To do that, we cut our genus 3 surface into 2 t-shirts. And we are going to construct on each t-shirt a convex projective structure with totally geodesic boundary. Actually, we're going to put the same structure on each t-shirt, and then we are going to glue back the t-shirt together to obtain a convex projective structure on the genus 3 surface. So we're going to focus on one t-shirt from now on. Each t-shirt is also cut into 2 octagons following this path. So we get in total 4 octagons. Okay. So let us consider, for visualization purpose, a finite volume complete hyperbolic structure on the interior of our t-shirts. By putting on each octagon minus the 4 green boundaries, we're going to we identify each of these octagons with a ideal regular square of the Poincare disk, and then we glue them together in the most elementary way you can think of. Interior. The reason why we put so finite volume t-shirt. The reason we do that is to 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 have a nice picture for oops, for the universal cover of our t-shirt. Yeah, also we fix one boundary component, one curve, which is one boundary component of our t-shirt. Let us call it alpha. It will be useful later on. And which identifies with the parabolic transformation of the Poincaré disk here. Okay, now that we have this nice picture of the universal cover, let us look at another hyperbolic structure on S, which is a bit wilder. And this hyperbolic structure, we obtain it by identifying our ideal square with a bounded square this time. And we have a developing map this way. So other hyperbolic structure. We identify the ideal square with a bounded square, and then we glue back the two bounded square. So several things about this new hyperbolic structure. The developing map here is not injective. Because, so I only drew here a finite number of tiles, of images of squares here. But if I were to continue, I would have to draw squares that overlap with our starting square here. And one way to see that is because now our representation of alpha is not anymore a parabolic transformation, but a rotation around this green vertex. So our hyperbolic, the developing map is not injective, the hyperbolic structure is not complete. So, and the holonomy is not discrete. So in this sense, it's a pretty bad hyperbolic structure. Maybe a last thing we can say is that this hyperbolic structure on the t-shirt, you can see it as the non-singular locus of a hyperbolic structure on a cone manifold. Which, on a cone manifold with 4 cone singularities, and which is homeomorphic to the sphere. So hyperbolic structure with 4 cone singularities. Here it's like that on the sphere S2. It looks like a pillow. Okay, so we have the non-discrete hyperbolic structure, and we are going to bend it to obtain something discrete and even better, convex. And we are going to bend it on the 4 geodesics we see here on the pillow, the 2 yellow geodesics and the 2 orange geodesics. Okay, so the bending procedure, let us call it, let us draw it in purple. We're going to bend. So we bend along yellow geodesic with parameter a big parameter t, given one, and we bend along the orange geodesic with the opposite, I mean the inverse parameter, t minus 1. Okay, let us have a look at what happens for a few tiles. Maybe to the 5 first squares, the central square, which doesn't get changed, and the 4 adjacent squares. Bigger. Okay, this looks nice. So now we are in the Kleinian, of course, Kleinian model in the projective space. So square has straight sides. So with dotted lines, you can see the 4 adjacent squares before bending, and then the filled lines are after bending. So on the up and bottom squares, we are bending with a big T, big parameter, so it means we're stretching like this. And on the lateral squares, left and right, we are bending with a small parameter, so we are compressing. Yeah, I forgot to say, let us give a name theta to the angle here of the starting polygon, the hyperbolic angle, I mean. And since we're starting with a regular square, this angle is the same on each corner, and it's strictly less than pi over 2. Afterward, in the projective space, of course, angles don't have meaning. Yeah, and here we have the bent representation of alpha, which sends our compressed square onto the stretched, dilated square here. Okay, so this is what happens for the 5 first tile. It's pretty easy to comprehend. Now let us look at what happens if we go into depth 4. Here it's depth 1. So the first square is depth 0, and then the 4 adjacent square is depth 1. Let us go to depth 5 with a nice GIF. Okay. So it becomes a mess at first. It becomes more complicated, but then if you wait long enough, it becomes convex. Yeah. Okay, we're done. Yeah, I like to look at it. We can watch it maybe 2 more times to try to understand what's going on. We start with something round, a lot of overlapping, as I was saying before. Then the squares becomes big after bending, and then it becomes small again. Okay, I guess that's enough. Let us try to understand why it should become convex. What is going on in this picture? And for this, we're going to focus on just the holonomy of rho t, alpha, and what's going on around this vertex, green vertex here. So to have at least a local picture there. So we centered our picture at the green vertex. And we obtain something like that. So we have 5 squares. We have, let me hit, oops, sorry. Here we have a square Q0, the starting square. we have the initial square before bending Q1, and then after bending Q1 prime, and on the other side, Q2 and Q2 prime. And so Q2 prime is obtained by stretching Q2 along a vertical stretch, Ft. And Q1 prime is obtained starting from Q1, doing a compressing from compression with a different axis. The axis is obtained by rotation of angle theta from the vertical axis. Okay, and so we want to use this information to compute the holonomy of alpha, the bent holonomy. And what do we know? Well, we know the holonomy of alpha sends Q1 prime onto Q2 prime, right? Rho T of alpha. And what else do we know? We know that Q2 is obtained from Q1 by just the holonomy of rho 0 of alpha, which is twice the rotation of angle theta. And hence, and we know, so Q2 prime is obtained by stretching Ft Q2, and Q1 prime is obtained by compressing Q1, so r theta minus 1, Ft inverse r theta of Q1. And using all this information, we get Q2 prime is equal to Ft r2 theta or theta inverse Ft r theta Q1 prime, which is Ft r theta Ft r theta Q1. Hence, rho t of alpha is equal to Ft or theta Ft or theta. Or rather, since we did some Roth recentering operation, or rather, we know at least that rho t alpha alpha is conjugate to this product of four matrices. Conjugate. And this product of four matrices, we can compute it. So if you take a suitable basis, Ft is just 1, t, and r theta is 1 cos theta, sin theta, minus sin theta, cos theta. Yeah. So this can help us to show that since t is very big and theta is 3 greater than pi over 2, rho t of alpha is Loxdroic, meaning it's diagonalizable with distinct eigenvalues. One eigenvalue being the green dot here, green point is the intermediate eigenvalue, and then there is one top eigenvalue and one bottom one top eigenvector and one bottom eigenvector, which are at infinity, which are not in this chart here. And so using this, we get the following local picture around the green vertex. So if we try to draw all the squares around this vertex, they are imaged by powers of rho t of alpha of the two original squares, and they win around and they remain inside some cone, convex cone based, sharp cone based at the green point. So this means we have local convexity. So it's in some way, in some sense, around our green point. Okay, and now there is a local to global lemma whose say the ID goes back to Weinberg, and it might actually be even older than that. Local to global convexity lemma. It implies that the whole thing is convex. The whole union of squares. Okay, let us look again at the nice GIF. Maybe now we have a better understanding. You can look at fix one vertex of the original square and try to see what's going on and see the squares around it. First, they all go around, and then at some point they are contained in some sharp cone. Okay. So last things I wanted to say. Yeah. So we have a convex representation, convex structure, but it's not enough actually for what we wanted. With more work, one can show that the structure we obtain is the interior of a convex projection manifold with totally geodesic boundary. So homeomorphic to the t-shirt with boundary, and whose boundary further satisfies a containment property that guarantee that if you double your structure, your convex projective structure, you obtain something convex and something closed. Okay, now what about higher dimension? So in higher dimension, one replaces the square by a hyperbolic manifold, a compact hyperbolic manifold with totally geodesic boundaries that meets at corners and totally geodesic corners. So if you have such a manifold and you double it, and you double it here, like for the square. So if you double the square, you obtain a sphere, a pillow, and here if you do that, you obtain more generally a compact hyperbolic cone manifold. Let us call it M. So let us consider such an object, and let us assume further that all corners of have angle at most pi over 2, strictly less than pi over 2, it's important. And the other assumption we need is that you can give colors to each totally geodesic component such that any two totally geodesic components that meet at a corner have different color. The fact that such a manifold exists is not obvious at all. So we give a construction based on common ideas in the topic of arithmetic hyperbolic manifolds, close, for example, ideas from Kapovich or Gromov. Sorry, Gromov and someone else whose name I forgot right now. And then, okay, if we have such a manifold, we can bend along the totally geodesic parts, and the whole procedure above works and will give you a closed manifold. I mean, a manifold, convex projective manifold with totally geodesic boundaries. Those boundaries are incompressible. They're pi1 embed in the pi1 of the whole manifold. And actually, they're also going to embed in the pi1 of the double. And those boundaries are homeomorphic to a product of a circle and a corner of the starting manifold. singularity of M, which is hence a closed hyperbolic manifold of dimension d minus 2. And because of that, our ending manifold will have a pi1 that contains Z2s. So it cannot be a world hyperbolic, and so it cannot be Anosov either. And this explains why the universal cover of the convex projective structure is going to be strictly convex. Okay, I guess I'm going to stop here and maybe show you another GIF with more tiles, too much tiles. Actually, we don't understand anything because so the depth is 8. And I'm gonna end the talk with that. So yeah, it seems not continuous sometimes, but it's just because uh, we would need to put more frames. The way all the polygons, the squares vary is continuous, of course. And here we go. Okay, maybe one more time and then we go off. Thank you again, Teddy. Go see Teddy's website and program.